Okay, we'll go ahead and get started. We'll go through and see how far we get into Chapter 17. We might push into next week. Next week is a shortened week, which means we might not cover all of Chapter 18, the electrochemistry chapter. I'm going to try and decide this weekend how far into it we'll get and announce that next week so we know where to cut off and you don't have to worry about for the exam. Okay? At very least, I think it's the last section of Chapter 18, electrolysis, we won't end up doing. I can almost guarantee that. Okay? I did finally look up the thermodynamic values. So if you look at Appendix 3 in your textbook, technically page A8, which is a pretty useless page reference, you'll see a list of a whole bunch of thermodynamic data. Those are all in the standard state. We're looking at entropy values, enthalpy, Gibbs free energy, and I think a couple others, but those three are going to be the ones, that's 3 fingers. That's 3 things that you're going to need to use for doing the homework assignments. So make sure you're aware of those. You are expected to look those up. Okay? When it comes to the exam, I'll give you those values, whatever I expect you to use. Okay? Pretty much all we covered yesterday was looking at the rules based on importance for determining the magnitude changes in entropy, be it positive, negative, those kind of shifts, okay, which is higher entropy, lower entropy. So you need to make sure that you know these rules and you apply them consistently. Start with Rule 1 and then shift your way progressively further through the rules until you find the one that actually identifies the difference. Okay? Do not go in the reverse because you'll end up applying the rules potentially incorrectly. Okay? So make sure you're careful with how you apply those. This is officially where we ended, though I kind of raced through it at the end, a bit mean. What we've been looking at or trying to put together is some understanding of an inherent energy. So when we looked at an individual figure, I think it shows up here. Okay, when we looked at the ball moving from position A to B, in physics we could explain points A and B based on potential energy. Okay? In chemistry, we don't really have that easy correlation. Okay? We look at distance, height, gravity, all those fun things in physics. We don't have that in chemistry. So what we've got to do is come up with some way to describe how we're transitioning between those 2 points and the energy associated with them. Because if we can determine that energy, we can start to predict different aspects of individual reactions. We're going to look at what conclusions we can get out of that. Okay, so that's the goal, is our inherent energy. Our first assumption was we could do that with enthalpy. Then it turned out enthalpy wasn't accurate enough. We could come up with exceptions to looking at enthalpy being our primary concern when we looked at individual reactions. Okay? So then we said, okay, well, there's other features to this. We could look at motion. We could look at some energy contribution from the temperature. Okay? And what we decided between that was when we looked at motion and temperature, they were related, and they're independent of our enthalpy. Because in most cases, we could predict a reaction based on the enthalpy. That means if we're going to set up an equation, what we'll do is separate those 2 terms through a plus-minus system as opposed to multiplication-division. Because if we looked at a reaction with 0 enthalpy change and we still saw a reaction occurring, our inherent energy isn't 0, which means something's got to be going on. Okay? So we have to have that additional term that's not directly tied into our enthalpy. Okay? So then the question becomes is how does that enter into our equation? Should we add or should we subtract this temperature entropy term? Okay? So let's go back to our initial theories and think about our signs on a good inherent energy. Okay? So this is where this figure comes back in. Okay? We said this one was the one that would be easiest to transition from A to B, or easiest to transition from reactants to products. What's the sign on our energy change there? Which is higher energy, A or B? A. When we calculate a change in energy, it's final minus initial. Which is our final? B. So a small number minus a big number gives us negative. So a good sign for our inherent energy has to be negative. Okay, so all we're trying to do is input what information we know to be true in each of these cases. Okay? What happens when we go to enthalpy? What's a good sign when we look at enthalpy? So remember, our inherent energy and enthalpy, we said were directly tied almost immediately. Okay? And we ignored the entropy term altogether. So let's ignore temperature and entropy. What sign does our enthalpy have to be to generate a negative value for our inherent energy? It must also be negative. So a good enthalpy sign is also negative. Okay? Now we can start to move into maybe, or not quite yet, the more difficult ones. How about the sign on our temperature? Okay, and you notice here it's not necessarily a good or bad sign, it's just what's the sign on our temperature. Well, what units did we decide to pick for temperature? Kelvin. Why Kelvin? It's always positive. We don't have to worry about a sign change on us. That makes our calculations a little bit easier. Okay? So this now brings us back to our entropy. When we looked at an individual reaction that actually occurred, okay, we put the ice on the table and watched it slowly melt at room temperature. Okay? That was a reaction that happened on its own. Okay? That was a favorable reaction. Okay? In the process of that occurring, what was the sign on the entropy change? Did our entropy go up or down as we move from ice solid to liquid? It went up. We increased motion of the individual molecules within the water sample. We're looking at a positive value for a good entropy. Why go through all of this? Well, ultimately what we're trying to figure out is that plus minus. What should that value be? Should it be a positive or a minus? Well, what we've now gone through and done is put in signs for pretty much everything. And we could now approach this and say, okay, what would give us the most negative value? So if we take our inherent energy and said that was negative, we said our enthalpy and wanted to be negative, and we said our temperature was going to be positive. Whoops, I don't know why I circled that. And we said our entropy was also positive. What does the sign have to be between those two equations to give us the most favorable reaction possible? So to be the most favorable, what are we looking at? Making it more negative or more positive? More negative. What does the sign in blue have to be? Has to be negative. Okay? So what we've gone through and derived is essentially an equation to represent now an overarching theory that sums up our inherent energy for any given reaction and ties it back to some other observables, an enthalpy, a temperature, and our entropy. Okay, so that's pretty huge as far as interpreting our energy for our reactions. Okay, so this equation is extremely important. We're going to come back to it in a little bit, largely because writing out inherent energy equals enthalpy minus temperature times entropy is an awful lot of things to put together and say. So we're going to want to shorten that into some symbols, and we'll look at that in a little bit. But before we do that, I want to take a look at some entropy calculations. So we'll finalize our discussion on entropy and then move into that overarching equation. Okay? So there are some extra laws of thermodynamics that we could evaluate. And what someone went through and observed, okay, and they probably did this mathematically first, is that when we look at the entropy of the universe, we'll notice that it's always increasing. Okay? That's not to say for an individual reaction we can't make the entropy decrease. We can do that. But what's the net result? If we decrease the entropy in one position, what happens? Entropy somewhere else has to go up. Okay? For instance, cleaning up your room or cleaning the kitchen, any one of those things. Those are a highly disordered state. Those make sense to be disordered. Okay? And depending on where you live, they stay disordered. Okay? Some people don't like it to be disordered, so what do? You go through, clean it up, and you organize it. what we've done is decrease the entropy in the kitchen or your room. How did we do that? Because according to our second law, our entropy needs to go up. We had to expend our own energy. Okay? That energy is being released in the form of heat. Depending on how messy everything was, you may have gotten really hot, tired. Okay? You've lost that energy somewhere else. So we're accounting for those differences. So when we look at an individual reaction, we see the entropy go down. That's fine. We can do that. We just have to realize that the entropy everywhere else in the universe has to go up to counteract that loss. Okay? And that's what the second law of thermodynamics is looking at. Okay? That relationship. They went through and narrowed that a little bit more. If we look at a reversible reaction, what we're saying is that the difference in entropy for each of those, for the system and our surroundings, is perfectly equal. Okay? So if we decrease the entropy of our system, we can increase the entropy of the surroundings, and the net is no difference. Okay? So a zero change. Okay? And that's something we've seen when we look at heat transfers. Okay? It's something that we assume when we look at heat transfers. That's how calorimetry works. For a non-reversible process, however, what ends up happening? Entropy always wants to go up, so what ends up happening is our positive, our up entropy value always will cancel out our negative, our decrease, and we always end up with a positive entropy. Entropy always goes upwards. Okay? Where does this really come into play? Perpetual motion machines, okay, all fail because of the second law of thermodynamics. Okay? How are we going to mathematically use this? We'll come back to how we got this equation a little bit. But if we take a look at an equilibrium reaction, okay, we'll take solid ice at 0 degrees Celsius. Okay, we add just enough heat to cause that solid ice to turn into water, liquid water. Okay? But because we added just enough just to transfer some of that across, what we could do is then remove some of that heat at the same time and reverse the reaction. Take our liquid water and turn it into ice. So what we can do is calculate the entropy change for each of these circumstances. If we add just enough heat to cause the ice to turn into water, we're going to look at the enthalpy of fusion divided by our temperature. Okay? Why does that equation kind of make sense? What are the units on enthalpy? Anybody? What are the units on enthalpy? Okay, a joule divided by temperature. What are the units on temperature? Kelvin. What are our units on entropy? Joules per Kelvin. Okay, so we do see a match there. We'll come up again with where that's coming from in a little bit. So if we take a look at the entropy change on going from ice to water, we can run all our calculations, look at the temperatures, say, okay, yes, this is the result we get. If we look at water to ice and we look at our entropy change, we'll notice all we get is the negative value of that initial value. Okay? So it completely cancels out. Our result is that this was reversible, and our delta S, our entropy in the whole, our total entropy ends up coming out as 0. So they cancel out. So it's a nice reversible reaction. Except when we go through to actually melt ice in the real world, do we have this control? Not really. So let's take a look at a potentially real world example. Let's take 37 degrees Celsius and we take our solid ice and we try and melt that. Okay, eventually what happens is we're going to take our ice to water, and that's going to convert at what temperature? What temperature? Okay, it'll be room temperature, or not, sorry, room temperature. It'll be the melting point for ice, which is 0 degrees Celsius or 273 Kelvin. So when we run through our calculations, we aren't going to be using this 37 degrees, our initial 37 degrees, to go from ice to water, because it's not where ice to water transitions. It transitions at 273. Okay? So we can go through and run that calculation, and we'll get a very similar value. Okay? Our entropy goes up. What happens in the entropy of our surroundings? Okay, well, the surroundings aren't at 0 degrees Celsius. Our surroundings were at what temperature? 37 degrees Celsius. So what we end up having to plug in is a different temperature value there. What's the net result? We get a slightly smaller decrease in entropy. So if we look at the total entropy for this whole process, both with our system and our surroundings, what do we notice? Entropy is positive. Okay, we add those two terms, our total entropy for our system increases. This would be the case for an irreversible process. Why is it irreversible? Okay, how many times have you successfully taken liquid water at 37 degrees Celsius and turned it into solid? Okay, 37 degrees Celsius is your body temperature. How often when you're walking around does your blood all of a sudden solidify? Okay, doesn't happen very often. Why not? It's looking at the natural tendency for heat to flow through reactions. We can't control that heat flow. Okay, so that's ultimately all we're looking at with our second law of thermodynamics. We can use it at phase changes because that can give us a boiling point of our compound. Again, we'll look at how we derive that or how we get that equation up at the very top. Come on now. How we get that equation a little bit later. Okay? So there's our second law. Entropy always increases. Yeah. So reversible and irreversible. In general, we can't control reversible reactions. We can try and set it up as close to reversible as possible. Because that simplifies our calculations. We can actually determine things a little bit better, a little bit easier when we look at a reversible reaction. However, none of our experimental systems are going to be able to mimic a reversible reaction perfectly. Okay, we can get close, but we can't get it perfect, which means ultimately we're just guesstimating as close as possible. We're using the reversible reaction to simplify our calculations and get results that make sort of sense or close to sense. The irreversible process is what happens pretty much in the whole world. Everything that we do ends up being irreversible. We can't control that heat flow, and that's what ends up resulting in everything being irreversible and our entropy increasing always throughout the universe. Okay? So as far as what we use it for, we're using it to simplify our calculations, and that's about it. Okay? Questions on the second law? Okay. Entropy and temperature. Okay, we've already looked at this a little bit, but we're going to look at it a little bit more detail to come up with the third law of thermodynamics. As temperature increases, what happens to our overall motion? It also increases. So we see this direct relationship between them. Okay, so let's try and see if we can come up with some quantifiable limits. So let's look at we could look at temperature, but before we look at temperature, let's look at entropy. What's our highest entropy? It's our lowest entropy. It's very difficult to put a quantifiable number on it. Okay, so let's shift to temperature. Can we do that with temperature? What's our hottest temperature? What's as hot as we can possibly imagine? This weekend? No, it's tomorrow, right? Okay, well then add 1 degree. That's hotter, right? So we'll go another degree, another degree. We can potentially get hotter and hotter and hotter through infinity. Okay? So we don't have a quantifiable hottest temperature, but what about a quantifiable coldest temperature? Okay. So we aren't looking at what happens at the end result of that's being so hot. But what we're saying is we don't have a quantifiable upper limit. Everything does, we would assume everything would ultimately decompose, but then what happens? Each of those decomposition things can still increase in energy and still increase. So we still don't, or we don't have a way to quantify that upper limit. So what about the lower limit? 0 degrees Kelvin. We do have that lower limit. Okay? And of course, leave it to the physicists to go through and prove that we can get lower than 0 degrees Kelvin. Okay? While they may have proved that we can get lower than 0 degrees, this is highly theoretical physics, have they gotten 0 degrees? No. It's very odd. I don't know how they've done it quite, but it's kind of interesting. They actually were able to get lower than 0 degrees Kelvin, but nobody's ever been able to get exactly 0 degrees Kelvin. Can't do it. Okay? So what happens to our motion if we hit absolute 0? In theory, everything stops. Well, if everything stops, what's our entropy? 0. Our motion is stopped. So what we can say for our third law of thermodynamics is that when our temperature equals 0, our entropy equals 0. Okay? Trying to think of any problems like that. I don't think I've ever asked a question where we can mathematically manipulate that at all. Again, I'm not positive. As far as questions you might see would be kind of like, which of the following is the third law of thermodynamics? Okay? So just looking at definitions and applying those. Okay? Questions about our second and third law? Okay. So before we get back into our inherent energy discussion, kind of a brief review over our enthalpy and entropies. Delta H is our symbol for enthalpy. Less than 0, it's exothermic. Less than 0 means it is negative. Delta H greater than 0 is endothermic, which means it is positive. We've got our Hess's law relationship, and this is something that we can use because it's a state function. The sum of the energy of our products minus the sum of the energy of our reactants, or enthalpies of our reactants, can get us the enthalpy for an overall reaction, okay? Or a new reaction. Those values can be found in Appendix 3, page A8, allegedly, within your textbook. Okay? The very last thing here, it's nice to go back to enthalpy. What did we decide was a favorable enthalpy change? Negative. We're looking at exothermic reactions being favored to actually occurring more frequently than our endothermic reactions. Okay? When we look at entropy, oh, I thought I had a different sum on here. I didn't. Oh well. We're looking at it being defined by the possible motions. Okay, so the more disorder, we have more motion. So when people typically think of entropy, you think of, oh, it's a measure of disorder. Disorder is kind of an odd term. Think of it more like motion. Okay, so if you got the idea of disorder from somewhere else, it really is better phrased as increasing the number of possible motions for an individual system. They're very related. They both apply the same. I just like motion a little bit more than disorder. I'm more optimistic, right? I don't want to be pessimistic with that dis in there. Then we've got our qualitative analysis rules. So this was looking at our phase changes, number changes. Shows how much I remember the rest of the rules. Complexity, and our mixtures. Okay? Entropy is a state function as well, which means we can still use Hess's law. Okay? Except now, instead of inserting enthalpy, so I didn't show that equation here, instead of using enthalpy in it, what can we use? Entropy. What's our symbol for entropy? S. Okay? So you can go through and look up entropies for your reactants and products and add them in a similar fashion. Okay? The units on our entropy as a new term, we get joules per Kelvin. And our second law of thermodynamics said our entropy was favored. A nice thing to summarize on there, which isn't on there, would be what is a favorable... Oh, that actually says it. Second law does say it. What's a favorable entropy change? Up. We're looking at positive entropies. Okay? That's ultimately what our second law says. We're looking for positive changes in entropy being good. Okay? We're going to come back to lots of pluses and minuses here. Okay? Before we push too much further into our equation, our inherent energy was a measure of whether that reaction could occur. And one of the words that we introduce is this idea of spontaneous. Does the reaction spontaneously occur? So if we put our ball, granted we should make that a little bit sharper. If we put our ball at position A, we would assume it spontaneously rolls to position B. Okay, in the case of 3. When we move up to cases 2 and 1, those are not going to spontaneously shift to our products. Okay? This is where we kind of run into problems with our our theory on thermodynamics, okay? And with our understanding of what the word spontaneous means. Wait. What? I just shuffled the slides and I thought I brought some slides forward. Okay, maybe those slides aren't there. So what we're looking at is spontaneous applying to a negative delta G. We'll come back to the word spontaneous in a little bit, because when we think spontaneous, what do we typically think of?
Random.
Happens. So if we say spontaneously combust, poof. Okay, we're already combusted. We're in giant flames. I'll tell you right now, you are all spontaneously combusting. Okay, why? Because the process of moving from our ordered state to our disordered state of carbon dioxide and CO2 has a very, very negative delta G. So spontaneous, in that case, says yes. That is a, sorry, not delta G, inherent energy. Okay? So we should all spontaneously combust. We are all spontaneously combusting. Why does that mean we even exist then? Because if we think spontaneous, we think instant, right? Poof, we should all be on fire. Why are we not all on fire? What's the rate at which we spontaneously combust? Very, very slow. When we look at our thermodynamics, thermodynamics is only looking at the energy difference between our reactants and products. So the energy here versus here. What does it not take into consideration? The rate, which is our activation barrier. Okay? So when we say spontaneous, all we're looking at is the relative positions of our reactants and products, not how fast the reaction occurs. Okay? And again, we'll come back to that. It might actually be in a couple slides here. So let's go back to our inherent energy. I've already made the slip up on it. It's a bit tiresome to go through and call everything by their full names. Inherent energy, enthalpy, entropy, temperature. So what do we come up with? Come up with symbols, okay, or variables that we can substitute in instead. Okay? So what we can go through and do is come up with some random variables to decide for this. We've already looked at our enthalpy, temperature, and entropy. Our inherent energy, so our overall energy for an individual reaction, is what we're looking at is a delta G. Delta G for Gibbs free energy. Okay? Gibbs happened to be the one that combined all of these energy ideas into one overarching concept. That's why he gets named for it. Okay? And because I think a bunch of the other letters were taken. Okay, so we've got Gibbs free energy. So that is what we're going to end up looking at for all of these. Now let's see, do we get back to spontaneous? Nope. Oh, here it is. So critical to understanding if a reaction can occur. Okay, it doesn't tell us when it occurs, it just tells us if the reaction is possible to occur. And we've looked at a couple circumstances where this happens. If delta G was less than 0, we said that was a favorable reaction. Okay, and that was something that we could visibly see. It doesn't mean all reactions are things that we can visibly see. The stuff that we visibly see happens to also have a relatively rapid rate. Okay, it goes fast. Our delta G doesn't give us information about that. It only tells us if the reaction will occur on its own given enough time. So when we see a negative delta G, then we say our reaction is spontaneous. It will occur on its own. If delta G is greater than 0, then it is non-spontaneous. Okay, the non-spontaneous one is a little bit easier to understand. That means if we leave that on its own, will we ever form products? No. So non-spontaneous makes a little bit more sense. That never occurs. Okay, we cannot get a non-spontaneous reaction to occur if we leave it alone. How can we get a non-spontaneous reaction to occur? We don't leave it alone. So we can go through, we can add heat. Okay, we could add a catalyst. So what we end up having to do is if we have a non-spontaneous reaction, we go through and total up our enthalpies and entropies according to this equation, and we don't get a negative delta G, what we'll have to do is try and tweak that reaction, those reaction conditions. Maybe if we just increase the temperature, maybe we can get the reaction to occur then. Okay? Maybe if we decrease the temperature, we can get the reaction to occur. So what we'll have to do on the non-spontaneous reactions is come up with some other way to force the formation of those products, our desired products. Okay? And that depends on what you're going to be working with. What happens at delta G equal to 0?
Equilibrium.
We're at equilibrium. Okay? Our forward reaction and our reverse reaction, or our spontaneous reaction and our non-spontaneous reaction, are now occurring at the exact same time. There's no favoring one way or another. We're looking at equilibrium. What happens at equilibrium? Just gave the answer up here already. What is delta G at equilibrium? 0, which means, let's see if I did it, we can simplify our equation to delta H equals T delta S. Okay. When is a reaction at equilibrium? How about a reversible reaction? In the case of a reversible reaction, we want to calculate delta S. What would we do? Delta S equals delta H over T. Where did that equation that we just talked about come from? It came from this one. Okay, and when we look at that phase transition for a reversible reaction, we can account for that phase transition perfectly. Okay? So that's where that equation is coming from. We will manipulate delta G at equilibrium to give us entropies based on enthalpies and temperatures. So you are responsible for using that equation as well. Okay? Questions about that? Okay, now let's see. Did I actually move it? There we go. I did move it. I just moved it to a different spot. Okay, when we're looking at our inherent energy or Gibbs free energy, we're trying to determine whether the reaction can occur. And this is where we come up with the terms spontaneous and non-spontaneous. If we look at a dictionary and we think about spontaneous, we think instant. Okay? If someone spontaneously combusts, the example we've been thinking about, okay, that usually shows up in the tabloids. Someone spontaneously combusted. Okay? Because that's this big, amazing thing. Someone just incinerated right in front of everybody else. Okay? So we tend to imply, at least according to our dictionary and our English understanding, that spontaneous means instant. In the case of chemistry, for whatever reason, it does not mean instant. It just means that that reaction can actually occur. It says nothing about the time in which it occurs, which is kind of an odd concept. So what we can do is switch to the non-spontaneous definition. Okay? So let's shift it a little bit. If we look at the negative, our non-spontaneous, that means our reaction never occurs. So spontaneous just means that it can occur, that it will occur at some point in time. That exact time at which it occurs is an entirely different issue. Okay? So be careful with what the meaning of spontaneous versus non-spontaneous means in our overall reactions. Okay? Questions about that? Okay. So we can go back to some manipulations now. I will mention that I am a big fan of these kind of manipulations. They will show up on your exam. Okay? Largely because you don't have to do any mathematics to solve anything. You can just go through and solve based on some simple numbers or some simple approximations. Okay? So as far as our rules go, if delta G is greater than 0, we're looking at a non-spontaneous reaction. Delta G less than 0, it's spontaneous. Delta G equals 0, we're at equilibrium. Okay? So what is the sign on delta G for a reaction where delta H is negative and delta S is positive? Why is this reaction fun, or this question fun? Because in any other circumstance, we could have numbers and we punch it into the calculator and just get an answer. Except if you don't know or enter into your calculator the right signs, you may end up getting it wrong. Okay, so what you need to do is be able to do this without numbers. So how do we do this? Let's see, I don't know if I put an answer up there. Oh, shoot. How should we go through and approach this? Do we know what delta G is supposed to be? Delta G equals R delta H minus T delta S, right? What did we say our delta H was? Negative. Okay, I don't care necessarily about the number, I just care that it's negative in this case. Okay, so our delta H minus T delta S, so let's do our minus sign. What's the sign on our temperature? It's always positive. What's the sign on our delta S? It says it's positive. So what happens? We take a negative number and we minus a positive number. That's the same as doing... Yeah, that is just subtraction. I was going to say adding a negative number. What's a negative number plus a negative number? It depends on your frame of reference. A more negative number. So what's the sign on our delta G? Negative. We don't need any numbers. If we plugged in numbers, it wouldn't matter what numbers we chose. Our delta G is always, every single time, going to come out to be negative. So that's kind of nice. If I know that the enthalpy is negative and the entropy is positive, there is no condition under which that reaction is not going to be spontaneous. A couple negatives in there. I think I got that right. Okay. Okay, so let's change up the phrasing a little bit. We got that one as a negative. What is the sign on the Gibbs free energy change if the reaction is both exothermic and disorder increases? Ooh, interesting. Now, instead of using all these symbols, we've switched it to English. So we've got to be a little bit more careful with this. What are we asked to solve for? Our sign on our delta G. So we have delta G equals. Okay, the first thing we've got would be our enthalpy, delta H. What is the sign on our delta H? How do you know it's negative? Because it says exothermic. Then we do minus our temperature, which is what sign? And then our entropy, what's our entropy? Positive. How do you know it's positive? It increases. What's the result? Same thing, delta G will be negative. I asked the exact same question in slightly two different formats. Okay? You need to be able to interpret each of those formats to come to the exact same conclusion. Okay, let's see if we can get another one. Is a reaction spontaneous if it is endothermic and the motions of the products are reduced compared to the reactants? Holy crap. What did we just ask for? Delta G. How do you know it asked for delta G? It asked if the reaction was spontaneous. Okay? For it to be spontaneous, what sign would I need to have? Negative. Okay, so what we can go through and do is determine what our delta G sign would be. Okay? Delta H, what's the sign on our delta H? Positive, because it's endothermic. Minus our temperature, sign on temperature. Okay? And we say the motions of the products are reduced compared to the reactants. Said another way, we decrease motion, which means has to be negative. Positive, what happens with these two negatives? Cancel out. A positive and a positive gives us positive. Is this reaction spontaneous?
Yes. No, it's not.
Yet another translation. Remember, we have to go to spontaneous. Spontaneous comes from our delta G. Delta G is greater than or less than 0? Greater than 0. If delta G is greater than 0, the reaction is non-spontaneous. Our answer in this case is no. Okay? 3 different ways to ask ultimately very similar questions. Okay? You need to be able to interpret these to make sure you can come up with those symbols and signs. Okay? You'll notice that we're getting a very similar question here, except the title changed. The title has changed now, temperature-dependent manipulations. In each of those cases we looked at, did it matter what our temperature was? No. Okay? We were always spontaneous or we were always non-spontaneous. There was no condition under which that changed. Okay? So let's go through another situation. Is our reaction spontaneous when it is an exothermic process, but internal motion is reduced? You got a new way to phrase everything. What are we asked to solve for? Ultimately, again, our Gibbs free energy. I think I actually stepwised this. Okay, what's our sign on our delta H? Plus our temperature. Okay, what is our entropy?
Why is that positive?
Why is our temperature positive? Oh, that's why you guys are saying minus. I was like, what are you talking about? Temperature is always positive.
It is.
Okay. Yeah, there we go. Negative. Thank you for catching that. That makes a big difference. Okay, what's our sign on our entropy? Why do we know it's negative?
Internal motion reduced.
We reduced our internal motions. What's our result? We get a negative. I always like to convert this into a plus in between. Negative times a negative gives us a positive. What's a negative plus a positive? Don't know. That's dependent on the temperature. Okay? If we have a very small temperature, how big is that positive value? Relatively small. So let's say our temperature, let's push to the extremes. Let's make temperature 0. What is our delta G? Negative, which means the reaction is
Equilibrium.
spontaneous at very low temperatures. Okay, now let's push it to the opposite extreme. Let's push the temperature to 1 billion. Really hot. What happens? Delta G will likely become positive. So when we go to ridiculously high temperatures, our delta G or our reaction becomes non-spontaneous. So what we're looking at is now a temperature dependence. Okay? You need to be able to recognize all of that. So I went through and subbed that through. In this case, we get that same kind of issue. Negative plus a positive temperature value. The bigger the temperature is, the more likely our Gibbs free energy is positive. The smaller the temperature is, the more likely our Gibbs free energy is negative. Yes?
Just leave it like that on the test.
So what would I ask on the test more than likely? So there's a couple ways we could do this. That's not a very easy question or a very easy format to put in as an answer. Okay, I could say, if we were looking at multiple choice, the reaction is spontaneous, non-spontaneous, equilibrium, or not possible to tell. What's the answer? Not possible to tell in this case. How else could we format this question? I could put in a bunch of numbers and say, at what temperature does it transition? So now we'd be able to plug in numbers for each of these, and where would that transition occur? Where would I go from negative to positive? What delta G value should I plug in? At. So if we're a negative number and we're going to positive, doesn't matter what negative number I use, doesn't matter what positive number I use, I will always go through the exact same point. What is that exact same point? Every single time. 0. So if we're going to look for a temperature dependence, we'll look at the point at which it transitions between, which is delta G equals to 0, and now we can calculate for temperature. Okay, I think I've got one of those problems up here. It for sure shows up in your homework. Okay. So again, I went through and picked some extremes. Forgot that I did stepwise through this. Okay. So what we end up discovering is that our reaction can be temperature dependent. It's temperature dependent when our enthalpy is greater than 0, and our entropy, or sorry, our enthalpy is less than 0, and our entropy is greater than 0. That looks swapped to me. That's negative and positive. That's not right. Oh. We'll go to that chart. For this summary, that should be negative, right? Yeah, that has to be negative. That has to be less than 0. Okay. Questions about that? Okay. Your textbook goes through and summarizes this in a slightly different format. Okay. This is a table that I would suggest is highly, highly memorizable, or highly recommended. I don't like recommending memorization. I wouldn't memorize this because I would do what we just walked through. Substitute pluses and minuses into my individual equation and see what the sign ends up coming out at. If you don't want to derive anything like this on the test, then what do you need to do? You need to memorize this table. Okay? And so what this table has done is ultimately derived all possible combinations. If we start with a negative delta H and a positive entropy, that was one of the very first examples we did. What happened to delta G? It was always negative, which means our conclusion, it is spontaneous at all temperatures. Our conclusion said further, or another way, it is not temperature dependent. That reaction will always occur. If we go through and now look at another possible combination, delta H being positive, delta S being negative, what's the result? Delta G will always be positive. What's our conclusion? It is non-spontaneous at all temperatures. Okay, why would that be relevant to a random chemist trying to go through and do stuff or do individual experiments? If we're trying to make a particular product and we go through and look at our thermodynamic values and we find it's non-spontaneous at all temperatures, is that a reaction worth trying to do? No, why not? It will never, ever occur. We would have to change our reaction conditions substantially to be able to get those actual products formed. Okay, so it makes a pretty big difference as far as trying to decide on what reactions you want to run. Okay? The next two are probably the trickier ones, in my opinion, because those become your temperature-dependent ones. They go through and evaluate for each of those cases. If we have a negative and negative, delta H and delta S, that means our Gibbs free energy can be positive or negative depending on the temperature. They again go through and give you conditions. It would be spontaneous at low temperatures, non-spontaneous at high temperatures. What happens if we switch positive and positive? We run into a similar situation, except now, at high temperatures, what happens to our reaction? It becomes spontaneous. So we see the reverse condition. Okay? Cannot stress enough how important it is to make sure that you've got this nailed down. This can help you solve an individual problem. Because if you've got it memorized, multiple answers, because all I can ultimately change with a lot of these are the signs, adding it up and multiplying in different formats. You could eliminate answers from the problem. If you know it's got to be spontaneous, your answer then has to be negative. So any multiple choice answer that is not negative must immediately be removed from your possible answers. Okay? So this chart is extremely helpful as far as processing and going through and analyzing these. Okay? Cannot stress that enough. Questions about that, actually? Not too bad? What do you guys think? Yes, no, maybe so. I rhymed. You should do fine. Okay. Gibbs free energy, just like our enthalpy and our entropy, is a state function. We can go through and use the sum of our Gibbs free energy of formation for our products minus the Gibbs free energy of our reactants. Okay? Just like we did with Hess's law, just like you could do with entropy. Okay? So a lot of the problems that I've noticed both within Connect and Sapling have you go back and look these values up to go through and calculate. Okay? In some circumstances, they can make it a little bit more difficult by tweaking the conditions so that you can't look up the energy of formation, or a Gibbs free energy of formation. So what would you have to do instead? Let's see. Nope, don't want that. If you don't know your Gibbs free energy of formations, but you still need to find a delta G, is there another way to get delta G? Yeah. Maybe they tell you the enthalpy for that reaction and the entropy, which means you can now solve for delta G in another format. Okay? So make sure that you're aware of these two different versions on how we can go through and get delta G. We're going to look at yet another version of it in just a second. Okay? One of the things that you might start to notice, or may have noticed already, is that little 0 showing up in both the Gibbs free energy expression and your enthalpy expression. What does that little 0 mean? Standard conditions. So when we go and look up our entropy terms and all those individual things, this material can, well, even before we do that, this material can be really, really confusing if we don't have something to compare everything to, because everything is ultimately a difference in energy. Well, if you don't know what your initial energy state is, how do you figure out a difference? Or if you don't know your final energy state, how do you figure out a difference between final and initial? So we have to incorporate some standard state. Someone went through and actually did that and calculated a lot of these variables around that standard state. Okay, so your standard state conditions suggest that gases are all at 1 atmosphere. Solids and liquids are pure. Why would that be important? That means they don't need to show up in equilibrium expressions. And solutions all have concentrations equal to 1. Again, why is all that nice? If we look at an equilibrium expression, let's say Kp, and we say all of our gases, so we've got gases on both sides of the equation, all of them are equal to 1. What's our product up top? 1 divided by 1. What does K become? 1. Simplifies our calculations. What if all of our concentrations were equal to 1 molar? What happens? K value again becomes 1. Okay? Technically our Q value. Okay? So it can simplify our calculations a lot as far as the material goes, which should start to give you a slight panic attack, because I just brought in the concept of equilibrium constants, which means, guess what? They're going to come back. Okay? Thankfully, no ice charts, but we will still have to do mathematical manipulations and see how delta G, our Gibbs free energy, is related back to the equilibrium constant. Okay? The one extra thing that is set when we're looking at our standard states is the temperature for that standard state expression is usually set at 25 degrees Celsius. Why do I say usually? Okay, we've talked about this before. Chemistry is a very large field. Lots of different people have contributed to it. Engineers, physicists, mathematicians, biologists, chemists. Depending on what they were working in, they set their standard state to whatever temperature they felt like. Okay? And they said, well, this is my standard state. Okay? If we compared this back to STP, which we saw in gases, what was the standard temperature for gases? Actually, I already forgot. Wasn't it 0? 0 Kelvin? Anybody remember that? Wow, your memory is just as bad as mine. That doesn't bode well. Okay? So standard states vary depending on different circumstances. You need to make sure that you're aware of that. Okay? Just as an example, my wife and I went through a bunch of calculations for one of her pieces of equipment, trying to figure out what was going on with different flow rates. Turned out the only thing that we messed up was I thought standard temperature was 0 degrees Celsius. She thought standard temperature was 30 degrees Celsius. You change the number, changes a lot of the results. Okay? So make sure that when someone's talking about standard temperature or pressure, that you know what standard temperature or pressure they're talking about. Okay, just because we called it standard temperature and pressure doesn't mean it's the same thing. Okay, which I know is irritating and frustrating, but that's the way it works. When we're dealing with thermodynamics, those are our standard conditions. Okay, so let's see. Now we're going to get into some fun stuff. Okay, this admittedly is probably only going to be directed at maybe 3 or 4 of you. Okay, I think this is extremely fascinating on how we can tie Gibbs free energy back to stuff we've already seen. Okay, so let's evaluate what we've seen here. What do we have drawn up? Curve, fair enough. It's an energy diagram. We're looking at transitioning between reactants to products. And when we look at thermodynamics, we said we're evaluating just the energy difference between our products and our reactants. The difference in energy there, despite what you'll see in textbooks, is the Gibbs free energy. Usually people will write in, depending on the textbook, you'll see it in organic a lot, instead of Gibbs free energy, delta H, or enthalpy. Why can we get away with that? No, it doesn't have anything have to do with the temperature. Anybody run calculations yet with your delta G's? Anybody look at the difference between your delta H and your delta S? What the units are typically? I know a few people have started, but you may not have seen it.
Delta G is kilojoules per mole.
Delta G we usually see in kilojoules. Enthalpy we usually see in... Enthalpy is actually usually shown in kilojoules. Entropy is shown in joules. The entropy contribution to most reactions is very, very small, which means in most reactions, delta G is roughly equivalent to delta H. Okay? So what they're doing is cheating you on the actual information. It is delta G. Sometimes we can equate that to delta H. Okay? For this material, we can't do that equation. Okay? So why go back to this? So our thermodynamics is looking at that energy difference. When we looked at kinetics, we looked at which part?
Activation energy.
We looked at our activation energy. Okay, ultimately that section. I should do that in a different color. Okay. Well, the activation energy is also a form of energy, just like Gibbs free energy. And if we go through and look at this curve, we might be able to determine a relationship between the Gibbs free energy and our activation energies, or the energies for each of these reactions. Okay? In particular, the EA that's shown here is the activation energy for what? The reactant or our forward reaction. Is there another energy difference on here that we could pull from our kinetics chapter? Do we have a reverse reaction possible? Yeah. That reverse reaction is the energy it takes to go from our products up to our transition state. So our energy reverse. What's the relationship between our forward energy, our reverse energy, and our delta G? We can see a subtraction between those two to match those up. It's not ER minus EF. Took me a little while to see that. It's actually the other way around. EF minus ER. Why? You have to account for the sign properly. So you'd have to make sure that your math added up correctly. So our delta G is equal to our forward energy minus our reverse activation energy. Okay, well that's kind of simple and basic, so let's make it more confusing. Do we know how to calculate our energy for the forward reaction? How did we get our energy for the forward reaction, our activation energy? There's some famous guy that came up with that relationship. Fun name, particularly if you slur his name a little bit. The Arrhenius expression looked at the relationship between our activation energy and the rate of a reaction. So what we can go through and do is now solve for the activation energy for our forward reaction and our reverse reaction from the Arrhenius expression. Okay, and this is where I think this gets very interesting. So first off, to be able to solve, our Arrhenius expression was K equals A e to the negative activation energy divided by RT. Okay, we wanted to solve for our activation energy. So what we're going to do, take the natural log of both sides and shuffle those down. So we can get the natural log of our rate constant for the forward reaction will equal the natural log of A minus the energy for our forward reaction over RT. What else can we do? Well, we also know that the natural log of our reverse rate constant is equal to the natural log of A minus our activation energy for the reverse reaction over RT. Okay. I decided to use an approximation when solving this that our natural log of A, our frequency factor, will end up being very, very similar. That simplifies our calculation. It's probably not exactly true, but we're going to assume it to be true in this case. So what we can end up solving for is we can get the natural log of our rate constant of the forward plus activation energy over R2, whoops, not R or A. We want our forward reaction will equal the natural log of our reverse rate constant plus, okay. Might be nice to group some similar terms so we can start to shuffle things around. RT minus forward over RT. Sorry, this is the first time I've done it on the iPad. It's not the easiest to fit all the space in here. Okay. Now what can we do? Is there an expression that we can do to simplify our left-hand side? Anybody remember those natural log simplifications? What can we get? The ln of K forward over K reverse. These are lowercase k's, which will become important in a second, which will equal negative 1 over RT times the quantity, whoops, forward minus E reverse. Yes? I did some mathematical shuffling there, and I usually do that backwards, so I think that looks right. What did we say EF minus ER was? Gibbs free energy. And we've got negative our rate constant forward over our rate constant reverse. We now have an expression that relates our rate constants to our Gibbs free energy. Right? That's kind of neat. Two concepts that are on opposite sides of our energy diagram are now tied. We can take it a step further. What is the rate constant of the forward divided by the rate constant of the reverse? A very particular instance known as the equilibrium constant. Okay. We now have an expression that can relate our equilibrium constant towards the energy for the overall reaction. Okay. While this derivation is not something you are responsible for, I think it's something that's interesting. There is a way to tie these two seemingly completely different topics to each other. The main reason why I go through and do this is because of the next slide. I think it's the next slide. The textbook throws this equation at you. Okay? And at first blush, you look at it, what the heck is that RT ln of Q? Where did that come from? What we just walked through and solved. Okay? Except when we're not at equilibrium, what is K? Q. Okay? So now given a reaction at any random concentrations or pressures, if I know the standard state Gibbs free energy, I can determine the Gibbs energy for that new reaction. Okay? Given any circumstances I want. Different temperatures, different concentrations, different pressures. Massively important for being able to find those relationships. Okay? That comes from what we just derived, seeing those relationships come out of it. Okay? In this case, R, remember we used R from our Arrhenius expression. R is which units? We need those joules. We're looking at the 8.3145. Why do I remember that number to that many sig figs? Okay? Our temperature is going to be in kelvins, and then Q ends up being our reaction quotient. So whatever conditions we happen to be at. Okay? Where do we get that delta G naught? Where does this term come from? Well, if we don't know it directly off, we've got two ways to go through and solve it. We can get that using a Hess's law relationship. We can look at the Gibbs free energy of formation for our products minus the Gibbs free energy of our reactants. Boom, we now have that standard state condition. Or if we know the enthalpy, the standard enthalpy and the standard entropy, we can determine that value. Okay? So we can then go through and apply this to pretty much any circumstance we want. Some interesting observations that fall out of this. What happens? That's not what I wanted. Yeah, we can go ahead and do that. What happens at standard conditions? Q is products over reactants. Standard conditions, what do we say the concentration of our products was? 1. Standard conditions, the concentration of our reactants. 1. Q becomes 1. What is the natural log of 1? 0. The Gibbs free energy, when we're at standard conditions, delta G equals the delta G at standard conditions. Wow, that's shocking. Okay? So we can then go through, our equation matches up with everything we've applied. We can now use this to our own advantage to try and solve for different expressions. Okay? Massively important, really, really kind of cool to see where it comes from. Okay? Or at least I think it's cool. Other interesting observation. What happens when we get to equilibrium? What is Q? Q now becomes K, because we're at equilibrium. What else happens at equilibrium? At equilibrium, the rate of our forward equals the rate of our reverse. So if we were going to draw an energy diagram, so here's my reactants, there's the transition state. What determines the rate? Our activation energy. So if we're now going to draw on our products, where should our products be? At the same level as our reactants. That way our rates match, because our rates are dependent on that activation energy. Why is that important? What's our delta G at equilibrium? 0. So we get two big conclusions that we can pull out of this. Delta G equals 0 and Q equals K. Do the substitutions in there, and what do we end up finding out? We can now solve for our delta G at standard states, ends up equaling negative RT natural log of K. Okay? Yet another expression that we can work with. This way, if we don't know the delta G for our overall reaction, or we don't know our equilibrium constant, but we were able to determine our delta G at standard states, we can now solve for our equilibrium constant. Okay? The Connect homework, at least while I was looking through it, went through and did a bunch of really odd equations to kind of tie a lot of these together, which I think is going to mean the textbook goes through a bunch of odd equations to tie them together as well. Okay? I think those are going to be pretty meaningless. Okay, so I'm not going to talk about those. I will take a closer look at the textbook to see what they're talking about, to see if they're doing those odd relationships. Okay? Ultimately, what you need to be able to go through and do is determine each of these variables. Okay, yes, this just went astronomically more difficult than what we've been seeing. All we had to do before was it positive or negative? Okay? But now all you have to do is plug in multiple numbers into an equation and just punch it into your calculator. Okay? So while it may look like everything's all of a sudden gotten more difficult, in most cases, you're given all of the numbers. If I tell you what the delta G at standard states is, what can you tell me? That was a lie. I tell you the temperature and the delta G. You can tell me what the equilibrium constant is. Okay? Given particular reactions, let's say a reaction, because I don't remember an actual reaction with real reactants. Let's say we start with a solid and we go to a gas. Let's push this a little bit further. What can you tell me if we're at equilibrium about the pressure of that gas? Would you be able to solve for it? What is the equilibrium constant for this expression? K equals products, which was our gas, divided by our reactants, which is solid, which means doesn't show up. So would you be able to tell me the pressure of that gas? Yeah. You could go through and determine your delta G at standard states, whatever the temperature was of the reaction. That gives you K. What do you know about the relationship between K and your pressure of your gas? Comes from the equilibrium expression. Okay? It's kind of bizarre how far back and forth we can run through these things. Okay? Your Connect homework and the Sapling homework both go through several examples. You'll have to decide when to use certain equations to apply them. I definitely don't have time to work a whole bunch of problems here. So we'll slide in some problems on Monday where we're looking at some more interesting dynamics of these. If that is the case, then I will go ahead and push the homework to Monday as well. Okay, so it won't be due Sunday. I would still highly recommend you go through and do that. A few adventurous students have already done the Sapling homework. That's before I finish today's lecture. Okay, which means you don't need to be in the or have this material to actually do the homework. You can do it all by using your textbook and applying the equations appropriately. Okay? I just generally talked about how we'd solve for the equilibrium constant. There we go. We can actually do it mathematically. I'm sure I'm not done. Okay, fine. I can be done. I don't actually know what stuff's on here next.